Hi everyone, I'm Kim and you can call me Teacher K. And for this short physics demonstration, we'll explore wave speed and transverse wave using a simple rope. So you might wonder or you might already seen waves when you shake a rope, watch ripples of water, or even observe light. But have you ever wondered how fast a wave travels through a material? That's why we call it wave speed. It is how quickly energy moves from one point to another through a medium. In this demonstration, I'll show you the speed of a wave changes depending on how tight or loose the rope is, and how is this concept connects to real life examples. So now, let's dive into the video.
Let's recall first. In a transverse wave, the particles of the medium moves up and down, while the wave itself travels sideways. So the motion of the particles is perpendicular to the direction the wave travels. Now, when we talk about wave speed, we're referring to how quickly this disturbance, or the energy, moves along the rope. There are two main factors that affect wave speed in a rope. First, tension. This refers to how tightly the rope is stretched. The greater the tension, the stronger the restoring force pulling the rope back to its original position, so the wave travels faster. Second, mass per unit length. This is about how heavy or thick the rope is. A lighter or thinner rope allows the wave to travel faster because there is less inertia to overcome, while a heavier rope slows down the wave. What's interesting is that the material and condition of the medium also matter. For example, a tightly stretched guitar string produces faster vibrations and higher pitched sounds. Also, a loose string vibrates slower and produces lower pitched sounds. That's wave speed in action. The same principle applies to our rope. Now, let's see this in action. I've tied one end of the rope to a fixed point, like a table leg, while I'll hold the other end. First, the basic wave pulse. I'll give the rope a quick flick upward. You can see the pulse move from my hand toward the fixed end. Right, that's the energy traveling through the rope. And it reflects back once it reaches the end. When the rope is tight, I will pull the rope tighter and flick it again. The wave moves noticeably faster. The tension is high, so the rope has a stronger restoring force. That's right, it can snap back quickly and transfer energy faster. Lastly, when the rope is loose. If I loosen the rope, the wave travels slower and it looks less defined. The rope absorbs more of the motion because it is not as firm, so the energy moves more sluggishly. No matter how I move the rope, notice that the rope itself doesn't move forward. Only the disturbance, or energy, travels. This shows that in waves, energy moves, not matter. Wave speed is more than just a concept. It's something we encounter in our real life all the time. Like in water waves, the speed depends on the depth and the density of the water. In musical instruments, like guitars and violins, the string tension and thickness determine the pitch because they awake the wave speed. In earthquakes, seismic travels faster through dense solid rock than through loose soil. And lastly, in communication, waves like light or radio waves move incredibly fast because they don't need a medium. So, to sum it all up, first, wave speed tells us how fast energy travels through a medium. Second, it depends on the tension and mass of the medium. Third, in transverse waves, motion is up and down, while energy moves sideways. And lastly and most importantly, waves carry energy, not matter. That's right. That's the beauty of physics. Even something as simple as a rope can show how energy moves through the world around us. Thanks for watching, and I hope this helps you understand wave speed in transverse waves more clearly. See you on the next videos. Bye bye!